Hello students, so in this lecture we will talk about the electronic band system in emission. Now the wave number arising from electronic transition is given as mu is equal to Te dash minus Te double dash plus G dash minus G double dash plus F dash minus F double dash, where T dash minus Te double dash, this is a constant for given electronic transition. G and G dash, G dash and G double dash, they corresponded to vibrational levels associated with different electronic states. And so we have different omega E, different vibrational constant and harmonicity constant for G dash and G double dash. These two are different from G dash and G double dash. Now, if we ignore the vibrational structure of the individual bonds, then the band origin of the system is given as U0 is equal to mu E plus D dash, function of mu dash, minus G double dash is a function of mu double dash, which is again equal to mu E omega E dash E dash plus 1 by 2. This corresponds to your G dash mu dash minus omega E dash, there will be a plus here, into V dash plus half whole square. So this corresponds to this whole corresponds to G dash U dash, and there will be minus omega E double dash V dash plus 1 by 2 minus omega E double dash V dash plus half whole square. So this later part corresponds to G dash U dash. And now for the electronic transition, there is no restriction on the change in the vibrational quantum number. So no restriction on V, which is the vibrational quantum number. It means that V is unrestricted. It can take any values. This means that the principal transition from each vibrational level of the upper electronic state can take place to each of the vibration levels of the lower electronic state. So each level can go to the all the levels can go to each of the levels in the lower state. Thus, we can expect a large number of bands from a single electronic transition. Now, considering the rotational structure of electronic bands, rotational structure of the electronic bands, the fine structure of the individual bands is attributed to the rotation of the molecule. So fine structures attributed to the rotation of molecule. So as you know, the electronic energy is the highest, then the vibrational energy, then the rotational energy. So fine structure arising is due to the rotation. Now if we take the wave number of line J dash, considering J dash and J double dash corresponding to rotation between the higher and the lower state. So we get wave number as equal to D dash minus E double dash plus F dash minus F double dash. So which can be written as equal to mu0 plus F dash J dash minus F double dash U double dash J double dash, where mu0 is actually equal to mu plus G dash minus G double dash. This is the band origin. And mu is equal to mu0 plus V dash nu J dash into J dash plus 1 minus V nu double dash J double dash into J double dash plus 1, and these two are again the rotational constants. So the rotational constants for the two states, for the upper and the lower states. So the selection rule is delta J is equal to R plus minus 1. So based upon that, we have the following transitions taking place. So if we have two different levels, this is the lower state, 0, 1, 2, 3, 0, 1, 2, 3. So there are two states. This is one sigma state. This is another one sigma state. So transition between take place between two. So take this one as G dash and this one as G double dash. So here J dash should be one less then J double dash would be 1 less than D dash. So from 3 it will go to 2. So and again from 2 it will go to 1, and from 1 it will go to 0. So this corresponds to delta J is equal to -1. That means the final one is G dash is less than J. J double dash is less than J, and this is called the R branch. And the lines can be named as this corresponds to 2 line, because the final one is 2. This corresponds to R1 line, and this corresponds to R0 line. Whereas in the we have a center here. This is mu 0, and on the left hand side we get the P branch. In the P branch, this G double dash J delta J is equal to +1, and J double dash is actually greater than J dash. That means from 0 it will first go to 1. From 1 it will go to 2. From 2 it will go to 3. So this corresponds to the P branch. So we have 2 branches, one P branch and one R branch, one for delta J is equal to +1 and one for delta J is equal to -1. Now both the P and R branch can be written as mu is equal to mu 0 plus dash mu plus P mu double dash into M minus P dash mu plus P mu double dash into M square, where M is equal to J double dash plus 1. And it is equal to 1, 2, 3 for R0, R1 and R2 lines, and M is equal to minus J dash is equal to -1, -2 for P1, P2 and P3 lines, and M is equal to 0 for the band origin. And these are known as, so based upon this we can draw a diagram. It's called portrait parabola. It takes the shape like this. You have M versus nu. So for get a shape like this, if B mu dash minus B nu double dash is negative, and it is called red degraded. This is the R this is the P, and the value of M here is 0 here, and it's -4, -8, -12, and it's 4, 8, 12. And on the other hand, it's -4, -8, -12, and 4, 8, 12 are P, and this is called valid degraded band, where this value is positive. Now to find the vertex of the band, we need to differentiate. So it can be right mu is equal to mu0 plus p nu dash plus p nu double dash m minus p nu dash plus p nu double dash into m square. And so if we put del nu by del m is equal to 0, we get the value of m for the vertex. With a different color here. So m for the vertex, and it is equal to p nu dash plus p nu double dash divided by 2 b nu dash plus b nu double dash and by substituting the value of m vertex into this band equation, we actually get the value of head minus mu0, which comes out to be equal to minus b nu dash plus b nu double dash divided by 4 b nu dash minus b nu double dash. So this is the thing. Now let's do a problem on rotational spectra. So it has been asked that the rotation transition lines from j is equal to 0 to j is equal to 1, the absorption line occurs at absorption line of 1.153 into 10 to the power 11 counts per second in C12O16 molecule, and at 1.10 2 into 10 to the power 11 counts per second for Cn O16 molecule, and you have been asked to find out the mass number N of the carbon isotope. So we'll first start with the fact that the mass of C12 is 12 mass of hydrogen, and the mass of O16 is 16 the mass of hydrogen. Since the constant of the bond involved in a CO molecule is not affected by isotopic substitution. The isotopic substitution has no effect on the constant. So we can write the constant K is 4 pi squared mu1 squared mu1 dash, and it is equal to 4 pi squared mu2 squared m2 dash, where mu1 is the frequency of the absorption line for C12 16, and m1 dash is the reduced mass of C12 16. So that's why m1 dash happens to be 12 into 16 divided by 12 plus 16, and it comes out to be equal to 192 by 28 atomic mass unit. Now for NO16, M2 dash is 16N divided by N plus 16. So if you substitute this value and this value into this equation, then we get uh, 16n divided by n plus 16 is equal to 1.153 into 10 to the power 11. Actually, it's the equation is actually m2 dash is equal to mu1 by mu2 whole squared mu1 dash. So m2 dash happens to be 16n divided by n plus 16, and it is equal to, if we put the counts, it has been given 1.153 into 10 to the power 11 divided by 1.102 into 10 to the power 11 whole square into 192 by 28, the 1 dash value. So it comes around 7.5065. So the value of N comes around 14.14 atomic mass unit. So this is the solution of CnO16. This is the value of N. We'll do another problem that it has been said that the force constant of the bond, there is a bond CO, the force constant, that means the value of K, is 187 newtons per meter, and its reduced mass m dash is equal to 1.14 into 10 to the power minus 16 kgs. This is for the CO molecules. What will be the frequency of vibration? It's very simple. So we simply have to write the formula. So omega is the frequency, and it is equal to K by m dash, and it is nu will be 1 by 2 pi K by m dash. So we put the values. So 1 by 2 pi over 187 divided by 1.14 into 10 to the power minus 16. So that is equal to 0.04 into 10 to the power 12 counts per second. So the separation between the vibration energy, we like to find out the separation between the vibration energy levels. So that is delta E, and that is equal to E plus 1 minus E nu, and it is equal to H nu. Simply have to write 6.63 to 10 to the power minus 34 joules second multiplied by the value of nu that we have obtained. It is 2.04 to 10 to the power 12 cycles per second, and we get the value of separation as 8.44 into 10 to the power minus 2 electron volt. So this is our